Okay, so we have now talked about the precise definition of a limit and worked through a couple of proofs of specific limits using that definition. What we haven't addressed yet are the other types of limits that we've dealt with in Chapter 2 so far. So for example, we have one-sided limits, left-hand and right-hand limits. We have infinite limits. What does it mean when the limit as x approaches a of some function f of x equals infinity or negative infinity? Our precise definition that we've talked about so far doesn't account for these. So we would have to come up with alternative definitions, but kind of similar looking to our previous precise definition for each of these cases. Now, we're not going to do much with these. I'm actually not going to do any examples using the definitions of the left and right hand limits specifically. We will do one example with an infinite limit. So I'm just going to briefly talk about these. For the precise definition of a left-hand limit, remember, we're looking at something of this form. The limit as x approaches a from the left of f of x equals L. Now, we'd want the definition to look really, really similar to our precise definition of a two-sided limit. But the difference here is that we are only allowed to approach a using values of x that are less than a. So remember before, we showed that in the precise definition of a limit, that condition here that said that 0 is less than the absolute value of x minus a, which is less than delta, was equivalent to saying that x is between a minus delta and a plus delta, with the added assumption that x could not equal a. That creates that interval, but that interval contains values on either side of a. In the case of a left-hand limit, we only want to use values that are smaller than a, or to the left of a. And so we're going to replace that condition with this inequality. X has to be greater than a minus delta for the delta that's mentioned here, but less than a. Notice that would mean x is only using, the only values of x we're allowed to use are smaller than a by this condition here, but that delta is still making an appearance here. Other than that, the definition looks pretty much the exact same. Right-hand limits have a similar alteration. Notice x is going to be between a and a plus delta. So this allows us to only use values of x that are to the right of a as opposed to the left of a. And again, like I said, it's not really important for you to fully digest these definitions because we're not going to be using them. I'm really kind of just putting them here for reference. Let's take a look at infinite limits. These ones, the definitions look slightly different. So for this guy, let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then the limit as x approaches a of f of x equals infinity means, notice the beginning of this starts the exact same way as our precise definition of a limit. All these conditions were pretty much word for word what we saw in the original precise definition, with the exception of that infinity there. What this means is that for every positive number m, there is a positive number delta such that if x minus a in absolute value is between 0 and delta, then f of x is greater than that positive number n. So this part looks different. Notice we don't have this inequality appearing anymore. Try to think of this logically. So remember what this means. This means that we have a vertical asymptote at a, and that our function is just becoming arbitrarily large as x gets closer to a. Well, to make x close to a, we would take delta to be a small number. And what this means is that no matter how small we make delta, we can always, let me say that slightly differently. As delta gets smaller, f of x is just going to increase without bound. It's going to get infinitely large. That's technically not the right term because you can't get infinitely large, but arbitrarily large is a better idea. Another way of saying that is f of x can be made larger than any positive number you want by taking x close enough to a. Okay, so hopefully that kind of made sense the way I explained it. Negative infinity, if I have the limit as x approaches a of f of x equals negative infinity, notice the definition is very, very similar, but this inequality changes. We're using an n instead of an m. There's no real reason for that. It's just the way that the author did it. But in this case, n is assumed to be a negative number, and no matter how small of a negative number it is, meaning towards negative infinity, we can always make f of x smaller than that by taking x to be close enough to a. So this is showing that f of x will be tending towards negative infinity as we approach a. I would like to just do one example proving one of these infinite limits. This one in particular. Prove that the limit as x approaches 1 of 1 over x minus 1 squared is equal to infinity. Now think of this one logically for a second. If we are approaching 1, if x is approaching 1, then the thing in parentheses here is approaching 0. So for example, if this is equal to 1.01, 1.01 minus 1 is 0.01. Squaring that, we get an even smaller positive number, and that small number in the denominator means that this rational expression of this fraction is going to be very, very large. And naturally, it makes sense that as x gets closer and closer to 1, this becomes a larger and larger positive number. Positive because we're squaring this down here. Okay? So what is it that we're looking for? Well, I want to let's do our preliminary work. Preliminary work on this guy. We want f of x, which let's actually, I'm not going to write it as f of x. We have our function. So I'm going to say we want 1 over x minus 1 squared to be less than some positive number m whenever this is true. X minus 1, that's what we're approaching, is less than delta. And I need to figure out what value of delta is going to make this work. Okay, so let me work with this guy a little bit. First of all, if I have 1 over x minus 1 squared is less than m, I can multiply both sides of this inequality by the x minus 1 squared that's appearing down here. And because it's squared, we know that it's going to be positive, which means we don't need to change the direction of this inequality symbol. I could also then, after doing that, divide both sides by m, which we also would be assuming is a positive number. It's in the definition up there. So I still don't need to change my inequality. This means that 1 over m is less than x minus 1 squared. If I were to then take square roots of both sides of this, square rooting both sides of an inequality will also preserve the direction that that inequality is facing. I would get this, 1 over the square root of m. Remember, anytime you take the square root of something that's being squared, the square root will cancel that second power, but it will always leave an absolute value behind. So we get this. Okay? Now this, let me see. I think I was using the wrong inequality. I need to change some things. So we needed f of x to be greater than m. I said less than m. I'm using the wrong definition. So that would be greater, greater, greater. Okay, so now look at, we found a constant that is strictly greater than the absolute value of x minus 1, which is the role that delta is supposed to fill. So we're going to set delta equal to 1 over the square root of m. Now we can write up our proof. My preliminary work got a little bit sloppy there. Sorry about that. Here's our proof. Okay? Let m be any positive number. And set delta equal to 1 over the square root of m. Okay? Now we make our assumption. We say assume, and remember we want to assume this statement here. Assume 0 is less than the absolute value of x minus 1 in our case, which is less than that delta that we defined here. Okay? Now I want to show that this is true. So to do that, what does f of x look like? So 1 over the absolute value of x minus 1 squared is equal to, now x minus 1 squared is the same thing as the absolute value of x minus 1 squared. Okay? Because in either case, the end result down here comes out positive, and it'll come out to the same positive number, so I can do that. Now, we have the relationship here that would say that the absolute value of x minus 1 is less than 1 over the square root of m. But if you take reciprocals of both sides of that, then that inequality switches places. So now, instead of, what am I looking for here? Let me see if I can write this off to the side. If I took reciprocals of both sides of this, then that inequality will trade places. So it becomes this: 1 over the absolute value of x minus 1 would be greater than that delta, which is 1 over the square root of m. And then squaring both sides would keep that inequality facing the same direction. And so what we're going to see here is, did I write that the right direction? I want to make sure I'm doing this correctly. Yes, that is what I wanted. This is equal, greater than 1 over the square root of m squared, because this thing is this thing squared. And this thing, when I square it, would look like this. This, of course, I'm sorry. I got that wrong. I'm taking the reciprocal of this. Sorry, I didn't work this one out ahead of time. I'm going to rewrite this. Sorry for the sloppiness. So, okay, 1 over x minus 1 squared is equal to 1 over the absolute value of x minus 1 squared, which would be greater than the reciprocal of 1 over root m squared, which would just be root m squared, which equals m. Okay, that's what we were trying to prove. So f of x is greater than m, and that's what this is saying right here. Sorry, I sort of botched that one up at first. Therefore, we can state our conclusion, which was that the limit as x approaches 1 of 1 over x minus 1 squared equals infinity. Okay. We're almost done here. So the last thing I want to do is really the most useful application of this precise definition, and that's proving our limit laws. Because so far the proofs that we've dealt with have been for specific functions, and all that work is going into proving just one specific limit. But if we can prove that any of our limit laws are true using our precise definition, then that means that we can use them with confidence, and we don't have to just take the author's word for it that they work. So this is your first limit law. The limit as x approaches a of f of x plus g of x is equal to the sum of those limits, provided that those limits exist in the first place. How do we prove this? Well, what we're going to do is suppose that the limit as x approaches a of f of x, we're supposing that they exist. I'm going to give it a specific value though, is equal to L. And suppose that the limit as x approaches a of g of x also exists, and we're going to call this one m. Okay? And then I'm going to say let epsilon be greater than 0. So remember, we always have this statement at or near the beginning of these proofs where we identify that epsilon greater than 0. Now, I'm not working with specific functions. I'm working with unknown functions, but we just have some information about them. We know what their limits are as x approaches a. Knowing that this is true as an assumption allows me to rephrase these limits in terms of the precise definition. So I can say this: thus, there exist a delta 1 and a delta 2 greater than 0 such that whenever this is true, x minus a is less than delta 1 and 0 less than absolute value of x minus a is less than delta 2, we have the absolute value of f of x minus L is less than. Now I'm going to do something here that's going to seem a little bizarre, but don't worry, I'm going to explain why I'm doing this. Epsilon over 2, and the absolute value of g of x minus m is less than epsilon over 2. So first of all, what was all this? What did I just write? Well, I'm basically using the definition, the precise definition for a limit, but I'm using it for two different functions with the same limit applied to them. So in both definitions, we're going to need x minus a is less than some delta in absolute value and greater than 0. But because I have two different functions here, the delta that I'm using for the f of x might be different than the delta that I have to use for g of x to make both of these statements true. So that's why I'm giving each delta its own name, delta 1 and delta 2, because they might be different by necessity. Now, the other probably puzzling thing is why I'm using epsilon over 2 here. Well, first of all, the statement of the precise definition of the limit says that this inequality has to be possible. We have to make this inequality true for any positive number that I could put here. If epsilon is positive, then so is epsilon over 2. Okay, but still, why am I using epsilon over 2? Well, that's going to become clear in the next step. Now, before we go any further, I want to state something that you should have learned at some point but may have forgotten. It's called the triangle inequality, because we're going to use this equality. The triangle inequality says that the absolute value of the sum of any two numbers, any two real numbers, is always less than or equal to the absolute value of A plus the absolute value of B. I'm not going to explain why this is true. It's not too hard to figure out why it's true, even if you're not doing a formal proof of it. If you just kind of think through this logically, but this is something that would have appeared in a previous class anyways. This is the triangle inequality, and we're going to need that here. So remember, what I want to do now is find a delta that makes this limit work. So I'm going to say let delta equal the min of delta 1 and delta 2. Remember, on that one example that we did in the last video, we had a similar definition for our delta. We had a min of, I believe it was 1 and epsilon over 5 or something like that. In this case, I'm setting delta equal to the smaller of these two deltas that I have here, okay? And then I'm going to say assume this, x minus a is less than delta, okay? If that's true, then I get both of these statements for free. Not for free. I get both of these statements as a result of that assumption. Right? And it's the same logic that we explained before. If delta is the smaller of these two, let's just say for a moment that delta 1 is the smaller of these two numbers, then assuming if we set delta equal to delta 1, then this assumption is the same thing as saying this. But if x minus a is less than delta 1, which is the smaller of these two, then it would automatically also be smaller than delta 2, since this is the larger of those two. So this assumption gives us both of these. These now, if we know that these are true, are what lead us to this statement right here. Okay? So now I need to set up the statement that's going to involve my epsilon. So now look at what the limit is that we're trying to prove. It's a new function that we get by adding f of x plus g of x. And we're saying that it should equal the sum of the limits of these two functions. Well, notice that would be the same thing as L plus m. So what I'm going to do is write this. F of x plus g of x minus what I'm supposing the limit would be, which is L plus m. Okay? Now I'm going to rearrange some terms here. This is equal to the absolute value of f of x minus L. Notice I could distribute the minus in and then rearrange some things, plus g of x minus m. Okay, and this is where I'm going to use that triangle inequality that I talked about up here. I have a sum of two things in an absolute value, these two things. My triangle inequality says that this is less than or equal to the absolute value, or the sum of the absolute values of these. F of x minus L plus g of x minus m. Okay, but we've seen both of these absolute values show up before. We saw those here, right? And I know that this one here is less than epsilon over 2, and this one is also less than epsilon over 2. So the sum of these two must be less than epsilon over 2 plus epsilon over 2. But that is equal to epsilon. So the end result of this is that the absolute value of f of x plus g of x minus L plus m is less than epsilon. By definition, what that means is this. Therefore, the limit as x approaches a of f of x plus g of x is equal to L plus m, but by definition of where we got L and m from in the first place, that's the limit as x approaches a of f of x plus the limit as x approaches a of g of x. And that's what we were setting out to prove in the first place. Okay? I've already said it a few times, 2.4, this entire section is a lot to digest. And again, we're pretty much not going to use this material throughout the rest of the course. It's important that you see it and that you understand that this is what a rigorous proof of a limit looks like. But for our purposes, throughout the rest of Calculus 1, after this section, we're not going to worry too much about the theory. Where this would become more important for you if you continued studying math is once you eventually go on to a course called Real Analysis, which is all theory, and it's very, very heavy on these epsilon delta type proofs. Okay, but that's it for 2.4.